Hello, everyone, and welcome to the third and final part of our three-part webinar series on what's new in SigmaXL version 10. I'm your host, Paul Petrin, and today I'm joined by John Noguera, the co-founder and CTO of SigmaXL. Today, John's going to demonstrate the new MSA Templates and Statistical Tools and answer all your questions at the end of the webinar. Participants will be muted, but please feel free to type in your questions. Note that support-related questions and questions not related to the content of this webinar should be sent to support@sigmaxl.com. So without further ado, please let me hand it over to John. John, the floor is yours.
Thank you, Paul. Welcome all to our webinar. As Paul said, what's new in SigmaXL version 10, part 3 of 3, new MSA templates and statistical tools. You can connect with me on LinkedIn. Here's my LinkedIn address. And of course, this is our website. Our agenda for today, we have an introduction to GageRR using general linear model. And then we will look at the GLM templates. First is the crossed, GageRR crossed with and without interaction. And then we'll start with a classical GageRR study just to get familiar with the methodology of using GLM to do GageRR. And then we'll look at GageRR with operator and one part. So a specialized GageRR. We'll look at nested or destructive GageRR. And then we'll look at expanded GageRR. So we'll use the templates to convert the output of the GLM to classical or traditional GageRR metrics. We'll look at orthogonal Deming regression. And then we'll conclude with the nonparametric Friedman and Friedman's exact, and the nonparametric two-sample Kolmogorov-Smirnov test, and the KS exact, which are an option in the Mann-Whitney dialog. These latter will just be brief, so just brief coverage of these. The main focus will be on the MSA templates. So to start, GLM can be used to analyze GageRR study data, and it provides much greater flexibility than a classical analysis, which can lead to measurement system solutions that otherwise wouldn't be found. This includes destructive, nested GageRR, and expanded studies with factors in addition to the traditional operator and part, such as test fixture or location. So GLM, general linear model, solves the variance components using ANOVA expected mean squares in the balanced case. And we talked about that in the second webinar. GLM can be extended using restricted maximum likelihood to provide confidence intervals for the variance components. And if the design is unbalanced, REML is used instead of expected mean squares. All right, so that's just a recap from last time. And same here, fixed versus random. The fixed factor includes data for all levels of interest. For example, there are only 2 test machines in a plant, whereas a random factor has levels that are randomly sampled from a larger number of possible levels, but interest is in all possible levels. And GageRR studies typically assume that part and operator are random factors. So it's important to note that in order to get variance components, you have to have random factors. Crossed versus nested. Classical GageRR studies are crossed, where each operator tests each part multiple times. An operator by part interaction may be calculated. And the example of the cross study is here, where each operator tests each part. All right, so that's your cross study. Your nested study have each operator testing unique parts. And typically you see that in destructive GageRR. And so because operator 1 tests part 1 and then part 1 is destroyed, it's not available for operator 2. So you cannot look at operator by part interaction. All right, so that's nested GageRR. So that was just a brief introduction to basic concepts. And so we're going to now use the AIAG study. Sorry, one more thing. This presentation assumes a basic knowledge of GageRR studies. So I'm not going to introduce concepts like repeatability, reproducibility. I'm assuming that these are already known, and because we're using more advanced techniques to get into the non-standard or non-traditional GageRR studies. But we will start with the basic, just to kind of show the flow of how it works. So I'm going to switch over to the data that's given to us from the AIAG manual. And this is a measurement which has 10 parts and 3 operators. Parts were measured in random order, but the worksheet is given in standard order. And what I'll do is I'll run first to start classical GageRR. So analyze GageRR crossed, and then part goes here, operator goes here, measurement goes here. We won't turn on the multivary, we'll leave that. But I will add a spec limit, upper minus lower of 8. So that will allow us to get precision to tolerance. And there's our worksheet. We see that both part and operator are significant. However, the part by operator is not significant. We see that the percentage of total is 28%. These are the confidence intervals, but 28% is considered marginal in a GageRR study. Less than 10 is ideal, 10 to 30 is marginal, and greater than 30 is unacceptable. This is our percentage of total, and this is our percentage of tolerance, 22.7%. And then we have our NDC. So again, that's your classical GageRR. So what I want to do now is I want to take the same data and analyze it using GLM. And then we can compare the results. So I go back to the worksheet. Now I go Statistical Tools, General Linear Model, Fit General Linear Model. The measurement is the response. There are no fixed factors here. Part and operator are random factors. And we'll use the default coding for categorical factors, -1, 0, +1. We won't use any of the residual or main effects plots. We're just doing, again, GageRR, analysis, sources of variation. And I'll click Next. I do want the main effects plus the two-way interactions. So I have part, operator, and part by operator. And that gives me my variance components report. I can see that part is significant, operator is significant, and part by operator is not significant. So same as the classical GageRR study. Here we have our variance components. And when we did the SOV studies in part 2, we focused on this table. Now in GageRR, well, actually, we'll still use this, but we will also look at the standard deviations as percentages. So this 19.68 is actually your repeatability. But the problem is we want all of the GageRR statistics. We want the reproducibility. And by the way, this is the reproducibility, the operator term, standard D percent of total. So that's the reproducibility and that's the repeatability. But we don't have things like the precision to total, the precision to tolerance, and that's what we want. These can be hand calculated, but the point of the templates is to just make it easier to extract your GageRR statistics from the GLM report. So to do that, we go Measurement Systems Analysis, Basic MSA Templates, and I can do cross metrics with interaction. I can do without interaction. So actually what I want to do first is, because this interaction is not significant, I'm going to rerun the GLM and I'm going to take out the part by operator interaction. In the classical GageRR study, that was automatically done. All right, the software automatically removed the insignificant interactions. So this takes us down to the report without the insignificant operator by part interaction. All right, so now what I'm going to do is I'm going to go measurement systems analysis, basic MSA templates, and I want GageRR crossed without interaction. So in order to use the template, I need to populate the part variance, the operator variance, and the error variance. So I come back here and part operator error. Okay, I grab these three and then I copy and paste them into the template. You don't need the total. I mean, it doesn't matter if you accidentally take the total, it won't do anything. It'll just come down here. So these are then used to compute the various GageRR metrics. Now we also need our process tolerance, which we had as 8, and that gives us our percentage of tolerance. All right, so you can see your percentage of total, 27.9, your percentage of tolerance, 22.7, and these match the earlier GageRR. All right, so we had the 27.86 and the 22.68. That's the use of the template. Now, obviously, if all you were doing was a classical GageRR, GLM would be overkill. All right, so the point of doing this was just to kind of build a bridge to kind of walk you through the steps involved. So let's now turn to a more interesting example, a non-traditional. What we're going to do now is we're going to say, what if we only had one part? All right, we have multiple operators, but we only have one part. So the way we're going to do this is we're going to use the Excel filter to basically just look at one part. Now, this isn't recommended. We're going to end up with basically 3 operators, 3 replicates, 9 data points in total. So that wouldn't be recommended for a GageRR study, but just for convenience, that's what we're going to do. So let's go back to the original data. And I'm going to use Excel's filter. And we're going to take part, and we're only going to use part 1. All right. So again, not recommended that you have a sample size this small, but for purposes of illustration, it'll do. It's convenient because we already have the data and we've already analyzed it. So clearly, a regular GageRR study isn't going to work because all the parts are the same. So you don't have part as a variable. You only have operator with replicates. So let's go Statistical Tools, General Linear Model, Fit General Linear Model. And we're going to do measurement. And part will not go in because basically there is only one part. We only want operator, and operator is a random factor. Everything else stays the same. So we click Next, select all, and run this. All right, so this gives us our variance components report. And these are the variance components, and these are the standard D percentages. So in this particular case, what we see is a pretty high percentage of total. But just because we have a high percentage of total, keep in mind it's a small sample size, but the percentage of total isn't really all that useful here. What is more useful will be the percentage to tolerance. And so for that reason, and to get the classical GageRR metrics, we're going to now kick in with our template. So we'll go to Measurement Systems Analysis, Basic MSA Templates, and we'll go to Cross Metrics Without Interaction. So the part is 0. So we'll just put that in a 0, and then I'll copy and paste the operator variance and the error term into the template. And here we can see total GageRR is 100%. Of course, that makes sense because there is only one part. So that's actually a meaningless metric. As the same with the repeatability and the reproducibility, they're not really very useful, but the percentage of tolerance is useful. And you get that here. You can see the 21.22 percent, indicating that this is a marginal measurement system. Okay, so that's again using the template to get your GageRR metrics from the GLM, the variance components report, and this is the example where there's just one part with multiple operators. All right, so now let's look at the case of a destructive test or a nested GageRR. All right, so this is a shear test for a resistance spot welding process. I have the reference. The references are given at the back of the slides in the PowerPoint. The design of experiments were used to produce the parts by varying preheat temperature, preheat current, welding temperature, and welding current. So they did a 4-factor, 8-run fractional factorial designed experiment. So essentially each run of the experiment is considered a part. And that was replicated 6 times for a total of 48 welds. They actually have 2 shear test machines. All right, so this is the actual welding machine, and they have 2 shear test machines. They do treat these as random in the paper, so I'm assuming there are other shear test machines available. So 3 of the parts go to machine A, and 3 of the parts go to machine B, and these will be treated as operator. All right. They actually measure both tensile shear strength and ultimate strain. We are just going to focus on tensile shear strength, so a single response MSA study. And the data is in tensile shear strength, so I'll go to that. This data is available under the help sample data. All right, so this is our shear test. This is the reference, so you can actually pull up the paper. It's open access publication. All right, so we're going to go ahead. Obviously, being a destructive GageRR where parts are nested with an operator, you cannot run classical GageRR. So we do statistical tools, general linear model, and we will select TSS, tensile shear strength, as our response of interest. Operator is a random factor, part is a random factor. And part is nested within operator because it's a destructive test. All right, once that weld is broken, it cannot be retested. Okay, so that's all our settings. Everything is default. We'll select all. So notice part parentheses operator. That's telling you that part is nested within operator. Two-way interactions would not be legal here because this is a fully nested design and part is nested within operator. So you cannot have an operator by part interaction. Part nested within operator is significant. Operator has a negative variance component and it's set to 0. So operator is obviously not important in terms of contributing to the measurement error. In terms of repeatability, you could use the standard dev of the error, percentage of total, but again, we're going to use the template to make it easier to convert the output of the GLM report into a more familiar GageRR report. This template is under MSA, basic MSA templates, GLM GageRR nested. All right, so here in the nested, we need operator, part nested with an operator, and error. So I take these 3, copy, and paste them into the template. Notice the negative variance component is converted to 0. we're not given a process tolerance in the original paper. So we have a percentage of total variation of 29.9%, so it's a marginal GageRR. Reproducibility, basically it's all due to repeatability. So again, that tells you that operator to operator, in that case machine to machine, does not contribute to the measurement error, but repeatability at the lowest level is contributing. Now, it's possible that, again, when you're dealing with a destructive test, it's a more difficult problem to separate part and measurement. But this is the format that you have that gives you an idea. So you probably would expect to get higher, say, percentage of total or percentage of tolerance than you would with a classical GageRR. It's just harder to separate out the measurement error from the process or part error. And these results, by the way, match those given in the paper. But so the whole idea here is just showing you the steps that are involved in converting that GLM output into a traditional GageRR report. And the last GageRR example is an expanded GageRR. Okay, so this one was from semiconductor. It's a wafer thickness measurement in angstroms for a semiconductor process. The design includes random factors batch, wafer, location, and operator. So you have batch to batch, wafer to wafer within batch, and location on the wafer within wafer. All right, so we have batch, wafer nested within batch, location nested within wafer, nested within batch. So reproducibility has operator, batch by operator, wafer by operator, and location by operator. So anything that involves the operator is part of the reproducibility, and the repeatability is the error term, all right, the lowest level. So this is our data, wafer thickness, so I'll open up that data. This is in the sheet, you have the reference. By the way, the paper is written in Korean. The information that's important is written in English, so you can still get the paper and extract the example from the paper, even though it is written in Korean. All right, so this is our data. Now we'll do the fit general linear model. And we're going to go thickness as our response. So we have all four factors are random factors. Okay, so batch, wafer, location. And then nesting, we have wafer nested within batch. We have location nested within wafer. Click next. And this time I am going to specify two-way interactions because anything that involves the operator is going to be a reproducibility term. So you have operator, batch by operator, wafer by operator, location by operator. All right, because operator is not nested within any of the other factors. So we'll select all. Oh, by the way, of course, so while you have these interactions, what you don't have, you don't see the wafer by batch or the location by wafer. Okay, those are illegal interactions because they're nested. So this part is nested and this part is crossed. So it's a mixed crossed and nested design. All right, so we'll run that. Okay, so we have our variance components report. We see that batch is significant, wafer nested within batch is significant, location nested within wafer, nested within batch is significant, but all of the terms involving operator are not significant. So that's actually a good thing from a GageRR perspective. This is our variance components report. There's a lot of terms here. You have batch, wafer, location, operator, the interaction terms. So again, to recap, anything involving operator is reproducibility. So what I'll do now is I'm going to open up the expanded GageRR. So this has more stuff. So the first thing I need to do, we're not given a process tolerance in the paper. So the first thing I need to do is I need to populate the error variance term. All right, so this is the part, it's a little trickier here, but you're converting a fairly complex output report into something that can be easily interpreted. I'm copying the error variance term into this cell. Then your part and process. So that's going to be the, I want the actual label, and I want to copy and paste here. All right, so these are the contributors to the part-to-part or process variation. And it is tricky, so you do have to be careful how you do this. All right, so we want operator. Anything that involves operator is going to go into the operator measurement source. All right, so now we have a clean delineation between the contributors to the part variation and the contributors to the measurement variation. In this case, anything involving operator is considered measurement error. All right, so that actually gives us everything we need, and the template has computed the percentage of total variation is 10%, which is very good, and that matches the number that was given in the paper. Okay, so this is the trickiest one. This is the expanded GageRR, and really the part you have to clearly delineate is what goes into the part bucket and what goes into the measurement bucket. All right, and that's based on your process knowledge. And then the calculations are done. They're simple calculations. It's just your classical GageRR calculations. But the GLM did the hard part, which is to get these variance components, okay, and to get the repeatability error term. All right, so that's the expanded GageRR. All right, so now we want to look at another template in the MSA called Deming regression or orthogonal regression. Now, orthogonal or Deming regression, Deming is the one who invented the procedure. It differs from simple linear regression in that it accounts for errors in observations on both the X and Y axis. So if I have, let's say, a supplier and I want to assess the measurement from a supplier to our measurement system, or we want to compare two suppliers, the thing is that there's measurement error on both. And if you just use a regular regression analysis, it's not going to fit the data correctly, because you could do Y versus X or X versus Y, and both would be correct in a sense, because they both have measurement error. X has measurement error and Y has measurement error. So orthogonal regression is ideal for comparing the same parts on two measurement systems. Okay, that's also important too, that you're comparing the same parts. So it's like a paired comparison. Now, unlike ordinary least squares, Deming's orthogonal regression minimizes the sum of squares of the residuals in both the dependent and the independent. And the residuals are calculated orthogonally. All right, in a classical GageRR, the residuals are computed vertically. But here, the residuals are computed orthogonally. And that then gives you a slope, and what you're looking for is a slope of 1. All right, if you have the same parts measured in two different locations, and statistically the slope is 1, then you have a match. All right, By the way, in Deming regression, this example is showing you a perpendicular. So that's what happens when the errors in X have equal variances. But you can actually change that. If you know, for example, that in-house we have less error than the supplier, you can adjust for that. So if you've done a GageRR study in-house and you have a GageRR study from the supplier, then you can actually compensate for the difference in measurement error. All right, and that's in this ratio, and we'll see that in just a sec. The fundamental assumption of Deming regression is that the ratio of the variances of the errors in the X and Y measurements is known. When the ratio is unknown, it needs to be estimated from the data using separate GageRR study or replicates. But you cannot simply use the variances from the data. All right, that is wrong to just take the variance of X and the variance of Y. If the measurement systems analysis is not available, the two MSA studies are not available and replicates are not available, then you would assume equal variances. So to run this is a template. This is the location of the template. But what we'll do is we'll just pull up an example that we have. SigmaXL, help, template examples, MSA examples, orthogonal Deming regression. All right, so basically you populate your X and Y data. So each row corresponds to the same part with two different measurement systems. And the important thing is that the null hypothesis for the slope is 1. Now you can change that if you want, but this p-value is testing the null hypothesis that the slope is equal to 1. So ordinarily in a regression, you're testing the null hypothesis that the slope is equal to 0. In this case, what you want to do is you want to fail to reject. So the fact that the p-value is greater than 0.05 and the confidence interval includes 1 is telling you that, yes, you do have a slope of 1. Okay. You can do residuals analysis. I'm not going to get into that. There are different types of residuals. You can look at that in the workbook to get more information. Also, you have a Pearson correlation squared, which is basically bivariate correlation coefficient squared. But also what is unique in SigmaXL is something called a generalized R-square. This was something that I'll just mention here. I'll just go to the references. So in this paper, they developed an R-square specifically for Deming regression. Okay, it's called the generalized R-square. They actually graciously provided us with our code, and we were able to validate that way. So we have a generalized R-square that's designed specifically for Deming regression. All right, so 93.9 is good. So you have kind of your classical Pearson correlation squared, and then you have your generalized R-square. That's the Deming regression. Again, the primary application is in comparison of measurement systems, where you have measurement error in both your X and your Y. Then let's go back to the PowerPoint. And as I mentioned, this part is going to be brief. So in the new statistical tools, we've added nonparametric Friedman. All right, so Friedman is an extension of the sign test. It's the nonparametric equivalent of a one-way repeated measures ANOVA. You might see references to two-way ANOVA. That's incorrect. All right, the Friedman test is not a nonparametric two-way ANOVA. It's a nonparametric one-way repeated measures ANOVA. And the concept is the same as that of a paired t-test. We're interested in the within-subject variability, not the subject-to-subject variability. And this would be a nonparametric equivalent alternate to a DOE model with blocks. If you wanted to do this in GLM, you would have one fixed factor and one random factor. The Friedman test requires exactly one non-missing observation for each level of the treatment within each block. The null hypothesis is that the medians are equal apart from the subject or block effect. And the alternative hypothesis is that at least one pair is different. This is actually a simplified null and alternative hypothesis. It's a little more complicated with ranks, but we want to express it and be consistent with our use of nonparametric comparison of medians elsewhere in SigmaXL. So the example, which I won't actually go through the steps, is given from the Conover book, Practical Nonparametric Statistics, where they have 12 homeowners, and each homeowner was asked to select 4 fairly identical areas in their yard and to plant 4 different types of grass, one in each area. At the end of the specified length of time, each homeowner was asked to rank the grass types in order of preference. So they're actually ranking. And then you run the Friedman's test in this case, and you have a statistically significant result. Okay, so that this is telling you that at least one pairwise set of medians are not equal. There is a difference in the preference of the grass types. There is a difference in treatment effect. We also have an exact version for smaller sample size, both the exact and the Monte Carlo exact. And that's just showing you in the Monte Carlo case, this is the Monte Carlo p-value and the 99% confidence interval for the Monte Carlo p-value. All right, that's the Friedman test. And then lastly, we've added the Kolmogorov-Smirnov test. All right, so this is not as well known. Most people know the Kolmogorov-Smirnov test as a normality test, but you can also use it for comparison of 2 samples. And what you're comparing is the cumulative distribution function, and it looks for the maximum distance, and it applies a test of significance to see if there is a difference. So the null hypothesis is that the distribution difference is 0. The alternative hypothesis, the distribution difference is not 0. All right, so you go through, and just to mention, it's built into the Mann-Whitney test. So if you're doing the Mann-Whitney 2-sample test, nonparametric Mann-Whitney, you have now the option, if you check this, display 2-sample KS. All right, and you get both reports. You get the Mann-Whitney and you get the 2-sample KS. Remember, they're testing 2 different things. So you're not necessarily going to get agreement always. Here we do have agreement. So the medians are different as well. The distributions are different. So just another useful measure. We also have an exact version of it. The exact is only Monte Carlo exact. And that's given here, and that matches the large sample. All right, so that concludes my presentation, so I'll turn it over to Paul.
Thank you, John. We'll now open up the floor to the Q&A portion of the webinar. John, here's the question. How would you analyze a GageRR study with both random and fixed factors?
That's a good question. I didn't cover that in this presentation, but if you open up the guide, so I have an example that does exactly that under, okay, so it's in the under the GLM. All right, so yeah, GageRR study with operator as fixed factor. All right, so this is under the general linear model. So in this example, what we do, we treat operator as a fixed factor. So you only have 3 operators. That's it. That's your entire population of operators. It's not a random sample. So this shows you how you would go about doing that. And in the GLM, you put operator as a fixed factor and part as a random factor. And so then when you run your variance components report, you'll notice one of the problems is because you put operator as a fixed factor, it doesn't show up in the variance components report. All right, so that's a tricky part. So now what you have to do is a hand calculation. And we show you here, you have to go to the regression model, and the steps are given here. But what you do is you use the coefficients. So you have the coefficient for operator A, you want to square that. The coefficient for operator B, you want to square that, but you also have to compute the hidden reference. And that's minus the sum of the two others. So you just basically sum the two others and square it. Then you take the average of the three variance components, and that gives you your fixed operator variance component. Sometimes if you have operator and technically it's fixed, and in a way that paper that I showed you where we had those two tensile machines, I don't think they have a lot of strength test machines. So they probably technically were fixed factors, but by treating them as random, it makes it easier to analyze because then you get the variance component calculated for you.
Thanks, John. This concludes the third and final webinar in our three-part series on the new features in SigmaXL version 10. We hope that you found this session useful and informative. As we conclude the series, we encourage you to continue exploring all the features available in SigmaXL and to reach out to us if you have any further questions or feedback. Your insights are vital to us as we strive to improve and evolve. Thanks all for joining us today, and we look forward to seeing you in future webinars. Have a great day.
Thanks very much. Thank you for your participation.